B2A Solutions is your trusted IT consulting company located in the heart of Europe. We design, build, and maintain scalable and user-friendly solutions tailored to your needs. Want to join a team that is shaping the future of the JavaScript ecosystem in Belgium? A team involved in the community by organizing events and contributing to open source? Join B2A Solutions now.
Speaker, ladies and gentlemen, is an engineer at Incidentio, and she's passionate about being inclusive and writes about tech, teams, mental health. I mean, there's a lot to write about, I think, lately. And she builds silly web apps, just because you can. Silly web apps. I love singing, so today's talk is Play Them Off keyboard app, which is, if I'm guessing correctly, a virtual keyboard in JavaScript. Ladies and gentlemen, give a big round of applause for our next speaker, Sophie Koonin.
Hi everyone, thank you so much for having me. I'm really excited to be here. It's my first time in Brussels. We haven't had enough technical problems yet, so I'm just going to test that the sound is working. Nope. That's not coming out of the right place. Let's figure this out. There's 4 different options for where the sound might come out of, so... Ooh. That's not good. And then try this one. Oh. Yeah. Okay, cool. So yeah. Yay. All right. So let's actually do the talk now. Oh, good. I love this. I'm really happy. Okay. Okay. Cool, never mind. Right, hi, I'm Sophie. I'm an engineer at Incident.io, not Incidentio, which is a Harry Potter spell. So we build we build software that helps companies manage and resolve incidents directly in Slack. So like we automate a lot of the process away, so you can just focus on fixing the broken thing. But that's not why I'm here today. I'm also a hobbyist musician. I'm a choir conductor, so I run a choir back in London. And I have a website, localghost.dev, where I write stuff about mental health and tech and things. And I'm also on Twitter, tweeting far too much at type__error. Still not going to work. Cool. So this is my virtual piano. This is a little JavaScript app. I say silly web apps in the nicest possible way. I think silly web apps are great. But I'm going to tell you today about how I built it, which involves going into the musical theory that went into it. And I'm also going to show you the API that powers it, which is the Web Audio API. But first, let's see what it does. So it plays scales. And it plays chords. Sorry about your ears. Brilliant. I think I've had enough of that. Cool. So how did this come about? My choir, that I mentioned before, has a holiday every year where we all go away together as a choir. We sing lots of songs, we drink lots of wine, there's usually some crying. But obviously, for obvious reasons, in 2021, we couldn't go away. Because of COVID, so we had a virtual retreat over Zoom. And I volunteered to run a workshop on musical theory. And the thing with virtual things over Zoom is that singing is impossible. I don't know if anyone tried it, but as a choir, we couldn't rehearse over Zoom. So I wanted to give people a way to put into practice the stuff I was teaching in this musical theory workshop. And I thought, what if I build a web app? It was also a great opportunity to build something fun and not actually build the workshop. So I'm going to start with a bit of musical theory, which is probably not what you're used to at a JavaScript conference, but I think it's fun. So we're going to talk about a bit of the science and the theory behind this app. And what I thought was really fun was a lot of the musical theory from the workshop that I gave actually went into the app itself. So starting at the very beginning, sound is made up of vibrations, and these travel as waves. And the number of those vibrations in a set time period is the frequency of the sound. And we measure frequency in hertz, and that's 1 vibration cycle per second. And if you think of a piano, the keys on the piano are connected to hammers, which hit strings, which are all tuned to vibrate at particular frequencies and make a particular note. And in Western music, we have a set of tones that have specific frequencies. And there are 12 notes. And in the US and the UK, at least, we have the letters A to G to name those notes. I know it differs in different countries. So we've got the 7 notes A to G, and then there's 5 notes in between there, those black notes on the keyboard. We call those accidentals. And those are really similar to the notes either side of them, so they don't get their own letter. And instead, we give them a symbol, depending on whether they come before or after the note. So they get like a little hash symbol, a sharp symbol. So we call them sharp if they are above the note. And then flat is before the note. So in fact, each accidental has 2 names. So A sharp is the accidental above A to the right of A, and B flat is the same note, but it's in relation to B. And we divide these notes up based on their frequency. So we're talking about a keyboard here, a keyboard being an electronic version of a piano, a lot smaller. A piano has 88 notes and generally starts from A, whereas a keyboard has 61 and starts from C. And those notes repeat in groups from lowest on the left to highest on the right. And these groups of repeating notes are called octaves. And so on a piano with 88 keys, you've got 7 1/4 octaves. And so I'm going to play you 2 notes. One is A in the 4th octave, and one is A in the 5th octave. And it's a weird ability of our brain that we can hear those 2 notes and kind of tell they're the same note, but not quite. They are exactly the same note, they're just a different pitch, so one is higher and one is lower. And in fact, each octave jump of a note doubles the frequency. So A in the 4th octave, the first note I played you, is 440 hertz, and A in the 5th octave is 880 hertz, so it's exactly double. And music tends to use some notes, not all of the notes. So in Western music, we've got a set of 7 notes that you can play from a note to reach the next octave, and we call that a scale. It's like a pattern that you can play to reach the next octave. And you think of scales a bit like a color palette. They have different emotions. So a major scale is like a happy color palette. And if you use the notes from this scale, your song is going to be a bit more upbeat. Whereas if you use the minor scale notes, your song might be a bit sadder. And music will use the notes of a particular scale in what we call the key. So if a song is in the key of C minor, then it will use notes from the C minor scale. And this slide shows 2 octaves of the C major scale. Don't worry, you don't need to know musical notation. The important thing to note here is that scales follow strict patterns. So this is the pattern for the major scale. I've shown you G major here. And we've got a pattern here that we can apply to any note on the piano, and it will produce the major scale for that note. Now, there's a few words here which I'm going to explain. So if you think of a note on the piano, so the ones with the green blobs are the notes of the G major scale. If we start at G, a note, one semitone is the distance between one note and its neighbor. You might know that as a half tone. And one tone, or a whole tone, is 2 semitones. So we've got the distance from G to A, that's a tone, 2 semitones. A to B is a tone, 2 semitones. Then B to C is a semitone. C to D is a tone. D to E is a tone. E to F sharp is a tone. And F sharp to G is a semitone. And that pattern, tone, tone, semitone, tone, 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 semitone, will give us every single major scale depending on where we start on the piano. Cool. So with that in mind, time for some JavaScript. Enough musical theory. So we are going to talk about the Web Audio API. Super cool. It can do all sorts of things. It can play audio. You can mix audio, analyze it, visualize it, create some cool Winamp visualizations in your browser. And you can also synthesize it, and that's what I've done. So if we recap that sound waves that we measure sound waves in their frequency is how fast they vibrate. Now, synthesizers generate these sound waves electronically to make sound. And that's what I've done. I basically built a little synthesizer in the browser. So what do we need to do this? Well, first we need what's called an oscillator. And this, in real life, is a circuit that produces an alternating waveform that emits a constant tone. We also need to define what that waveform looks like. So different waveforms will make different sounds. We need to know what frequencies to play. So we need to know the frequencies of all the notes on the piano before we can actually make them make sound. And finally, we actually need to build a piano interface that someone can interact with and play the notes. So where do we start? We start by initializing an audio context. And this is a function that exists on the window object in the big four browsers. And we only want one of these in the app. If we have more than one, we're going to start to get kind of mystery sounds where we don't want them. So we have one audio context. And then we need to create our oscillator. And handily enough, the audio context function gives us the audio context, which has a function called create oscillator. And obviously, it's not really a circuit. It's some JavaScript browser magic. But we connect the oscillator to the audio context destination, which by default is system output, so your speakers, your headphones. But it won't be doing anything yet. So different kinds of waves make different kinds of sounds. So I just played you a sine wave and a square wave. And the shape of the waveform will determine the sound that's produced. So like three really common waveforms are sine, square, triangle, and sawtooth. And these are all pre-built into the Web Audio API oscillator. But you can also provide an array of floats that make up a waveform. And I just got one off the internet. But basically, they represent points on a graph that map out a waveform. And so you can call the create periodic wave function on the audio context and pass in the two arrays of floats. And then that will register the wave with your audio context. Now, when you think of a synthesized piano in terms of things like GarageBand or other kind of MIDI players, you think, OK, that sounds more like a real piano. Well, they tend to use samples, so actual recordings of pianos. So it is possible to do that with this, but for the purposes of this project, I just wanted to synthesize a wave rather than actually use recorded sound. So now we've set the periodic wave that we created, and now we can call start. And what that will do will get the oscillator going and get the app playing a fixed tone. And it defaults to 440 hertz. So what if we want to do a different note? Well, we need to calculate the frequencies of the note on the piano, and we can do that using a formula. So here, I'm just going to draw attention to the note that I keep coming back to, which is 440 hertz, and that's A in the fourth octave. And it is a very special note. It's actually standardized as ISO 16, as the note to which you will tune an orchestra. And it's A above middle C on the piano, so middle C, right in the middle of in the fourth octave. And A4 comes a few notes after that in the same octave. And the reason why it's so special is because it's a really nice round number right in the middle of the piano. But this is going to be very useful for us. So the formula to calculate a note's frequency is based on its position relative to another note on the piano, one that we know the frequency of. And so it makes sense for us to use 440 hertz as a constant. The formula itself is 440 multiplied by 2 to the power of n over 12. So n here is the number of semitones between A4 and the note that we're looking for on the piano. For example, if we take the note C5, that's C in the 5th octave, higher than A4. If you count it out on a piano, that's 3 semitones. So there's like 3 keys in between A4 and C5. So this would be 440 multiplied by 2 to the power of 3 over 12. So let's translate that to some code. So this function takes a letter and a number combination, so that's the note letter and the number of the octave that we're working in, and it produces a frequency. So first, we need to get the interval between A and our note as if it were in the same octave. So A to C is -9, because C comes before A in the group, because we tend to go from C through to C. And then we need to get the interval between the octaves. So we want C in the 5th octave, but we have A in the 4th octave. So we need to calculate what the distance is between the 5th octave and the 4th octave. And then we multiply that by the number of semitones in an octave. And then we add those together to get the number of notes between our 2 notes that we're looking for. And then we run that equation to calculate the frequency. And for convenience, we round it to 1 decimal place as well, because life's too short to not do that. So now we've got enough knowledge to generate an array of frequencies for every single note on the piano. Cool. Now we need to build the piano. I built mine in React because it seemed like a good idea. Vanilla JavaScript would be totally fine too, and equally fun. So I ended up porting over a library called Piano SVG, which renders the piano, which was super convenient. And the way that I did it, each key is its own component and has an ID, which represents where on the piano it sits. So the one on the far left would be 0, and the one at the other end would be however many keys that is. I didn't count. But the piano itself sits within a component called a player. And this is what controls all of the audio operations. So manages what's playing and what happens when you click the different things. So there's a couple of different ways that you can interact with this. You can click the notes, and they will play once. But I also wanted to be able to hold the notes down. So I created a kind of sustain pedal, which is just a flag, effectively, in state. And so if the pedal is active, then you have these handlers that when you click a note, it'll just keep playing. And it sets the frequency of the current oscillator. So if we want, because an oscillator can only play 1 note at a time, if you want to just play 1 note at a time, then you can use the same oscillator. But if you want to have multiple notes playing at the same time, you need a new oscillator for every single note. So when you play a note, we initialize an oscillator, or get the existing one if it's already there, and then we set the frequency value to the frequency of whatever that key's ID is in the array of frequencies that we've got. So I had a few problems with this. So for one thing, sometimes the notes just don't stop. I literally had to put a disclaimer at the bottom that says, if it's broken, refresh the page. That's the beauty of personal projects. And I'm tracking all of these oscillators in state and disconnecting them when they're finished, but sometimes they just don't. And they're also a bit slow to initialize, so it's a synchronous function, but I had to wrap it in a promise because I would call it, and it wouldn't finish in time for me to actually start doing stuff with the oscillators. But yeah, decided you can just refresh and live with it. So I wanted to be able to automatically play the notes of a scale. And if we remember that scales follow particular patterns, this is fantastic. We love patterns, we're programmers. So if you think about the pattern, tone, tone, semitone, tone, 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 semitone, a semitone is 1 note and a tone is 2 notes. So we can just translate those to numbers. And then we can iterate through an octave, which is an array of frequencies. And we can add 2, 2, 1, 2, 2, 2, 1 to get all the frequencies of the notes in a scale. So we'll generate an octave of notes, and then we will iterate through that scale pattern. We have a cursor that points to the current position in the array, and then we add each note of the pattern and then get the note that the cursor points to. So it's like an index of that in an array. And to play the scale, we have one oscillator, because we just want to play one note at a time. And we change the frequency of that oscillator at regular intervals. So I set timeouts per note in the scale. We have about a half a second timeout, which I multiply by the index of the note in the array so that it staggers. And then when the timeout elapses, the oscillator frequency will change to the next note in the scale. And then we store all of those timeouts in component state so that if someone hits the stop button, we can just cancel them all and everything will stop. And for playing chords, so more than one note at once, we have different patterns and fewer notes, but it's the same principle. So rather than setting a timeout this time, we just create a new oscillator for each note and then set them all on at once, making sure that pedal flag is on so that we can sustain those notes. And that's all there is to it. You can find it and play with it at virtualpiano.vercel.app. And you can also find the code up on GitHub, which is github.com/myname/virtualpiano. Thank you very much.
Okay, also, yeah.
B2A Solutions is your trusted IT consulting company located in the heart of Europe. We design, build, and maintain scalable and user-friendly solutions tailored to your needs. Want to join a team that is shaping the future of the JavaScript ecosystem in Belgium? A team involved in the community by organizing events and contributing to open source? Join B2A Solutions now.